Hi, I'm Maraki, and in this video, I'm going to talk about my MSc AI individual project titled the Multilayer Counterfactual Explanations for Machine Learning Classifiers. So, what is counterfactual explanations? To illustrate the concept, we can start with just a simple example of a guy named John. So, he is just a typical bank customer, and like most customers today, whenever you interact with a company, oftentimes data about you ends up getting sent into some sort of model. In this case, if you are a financial institution, often these models are trying to predict things that you care about in terms of outcomes. So in our example, predicting whether John will have repayment problems. After some processing, the model decides for the bank to deny John's loan application. So then this leads to a question from John, obviously, like, why did you deny my loan? If you have a good manager, then he should really ask the same questions. Why are we making these really vital business critical decisions? One way to understand this decision is to then run a counterfactual explanation algorithm on top of the machine learning model. Counterfactual explanations provide explanations of the form of counterfactual instance, highlighting smallest change to feature values in order for a different classification to materialize. In this case, one example of counterfactual explanation would be if John's income was 45,000 instead of 30,000, then his loan would be accepted. The main output of this project is the novel state-of-the-art counterfactual analysis framework called the Approximate Layered Influence Counterfactual Explanation, abbreviated as ALICE. This algorithm is developed by me together with Emanuele, Antonio, and Professor Francesca Toni. Let's now formalize the algorithm definition, provide some intuitions, and demonstrate how it works. Given a machine learning classifier represented as 5 elements tuple and a distance function d, an n-layer explanations for the classification beta in an evaluation epsilon is an n+1 tuple such that the first element xr is the set of relevant variables to the classification beta. And the second two n+1 elements are the set of jth critical influences. The intuition for the layered critical influences is that ALICE categorizes features into multiple levels based on their criticality. The set of most critical features, or what we call as the first critical influencers, is a set comprising features in which if we change the features value while keeping the other features values unchanged is sufficient to obtain a change in the classification. For less critical features, for example, second critical influencers, the set comprised of features in which if we change the feature value, it would not change the classification, as at minimum we also need to change another feature to obtain different classification. The idea can thus be extended to n critical influencers, hence the name layered influences, in which the element of the set requires at minimum n-1 other features to also change in order to observe a classification change. To fully understand ALICE definition, consider the university admission example. Imagine that we are building a logistic regression model for a university to determine whether to accept or reject their applicants. The admission decision depends on 4 binary features represented by W, F, E, and G. W indicates whether applicants have work experience. F indicates whether applicants are first-timer. E indicates whether applicants pass entrance exam, and G indicates whether applicants met GPA requirement. For easy demonstration, I have included a table on the left that provides all possible classifications from our logistic regression for all combination of features. Let's now run ALICE to explain the decision for the plus minus case, which is classified by our logistic regression as minus or to reject this applicant. We observe that the explanation for this prediction is the set FG slash set E slash set W slash empty set. So what this explanation tells us is that F and G are first critical influencers, E is second critical influencer, and W is third critical influencer. Since F and G are first critical influencers, then this means that toggling F or G while keeping the other features unchanged will guarantee a classification change. To verify, we toggle F, resulting in the evaluation plus 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 minus, which is now classified by our logistic regression as plus or admitted. This aligns with our Alice definitions, as changing F alone is sufficient to obtain a classification change. Similarly, toggling G while keeping the rest of the features unchanged will also change the classification. This is consistent again with our definition. Now, we see that E is a second critical influencer. From the definitions, this means that if we change E alone, it will be insufficient to obtain a classification change. We verified this by toggling E, resulting to plus minus 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 evaluation, which the logistic regression still predicted as minus or rejected. But since E is a second critical influencer, then the definition tells us that there exists another influencer in which, if also toggled, we can detect a classification change. In this case, if we toggle G as well, it will result in the plus minus minus plus classification, which is now classified as positive. Finally, we observe that W is a third critical influencer. What this means is that if we toggle W, we require at minimum 2 other features to also change in order to achieve classification change. We observe that if we toggle F and G apart from W, we achieve this classification change as predicted. Apart from providing counterfactual explanations, Alice can identify features that are causal and non-causal for a decision. To identify the causal features, we simply take the union of all set of J critical influencers. Conversely, for non-causal features, it is the set of all features, F, minus the union of all set of J critical influencers. Taking this further, we can compute the causal responsibility score, calculating the degree of responsibility of its feature to an outcome. This score is simply calculated by taking the inverse of the set index of the set where the feature belongs. And if the feature is non-causal, then it's 0. This responsibility score provides a connection between counterfactual and feature attribution explanations. To illustrate, consider a real-world dataset example, the Congressional voting records. In this example, we are given 16 binary key votes to predict the party membership of Congress members, which can be Republican or Democrat. Our task for this example is to identify the causal and non-causal features, as well as to calculate the Alice responsibility score for its feature. We then run Alice, and we show the explanation in the form of an explanation graph, as shown in figure 4. Since all 16 features are either first, second, third, or fourth critical influencers, therefore, all features are causal to the decision, and no non-causal feature for this example. The responsibility score can be calculated by simply taking the inverse criticality level of its feature. For example, as MX missile is first critical influencer, the degree of responsibility is 1. Similarly, with aid to Nicaraguan contrast, duty-free export, anti-satellite test ban, and El Salvador aid. The handicap infant is the responsibility score for the handicap infant is 1/2, as it is the second critical influencers, and we can calculate the responsibility score for all features in the similar manner. The following are two primary contributions of this project. First, we develop a novel framework, ALICE, that is superior to existing frameworks in several aspects. Our framework overcomes the scalability limitation of the predecessor method CFX. And also, our framework provides very richer layered explanations compared to the predecessor method. While doing so, ALICE still maintains the desirable properties of CFX, in particular the uniqueness property, hence gaining inherent advantage of CFX over rival methods such as MCX and PIX. The framework also allows the generation of counterfactual examples that are superior to examples generated by the state-of-the-art methods such as Wachter et al., Phase, and DICE. The second contribution is our research discover connection between counterfactual and feature attribution explanation as we adapted the degree of responsibility into explainable AI. More specifically, ALICE can be used to generate feature attribution scores, suggesting the importance of its feature to a classification that are grounded in a novel concept, the actual causality. This is a novel contribution to the field and may foster further research, especially in the intersection between counterfactual and feature attribution explanations. We showed in the experimentation that these new feature attribution scores derived from counterfactual explanations are quite promising, as it attained comparable performance to the state-of-the-art famous feature attribution methods like LIME and SHAP. Thank you.